Alright, hi guys. Today's lecture is going to be about generative adversarial networks, or GANs. Um, and just to give you an idea about what they can do, the images that you see on the slide are actually generated images. These are not real people. Um, so GANs created these images. So hopefully that should get you interested. So let's get started. So a lot of the content in this lecture is from uh, Google's machine learning crash course. You can find this just searching up Google machine learning crash course online and navigating to the GAN section. And I think it's probably worth your time to check that out because it's super easy to understand. If you have a solid foundation about neural networks. Um, and so, yeah, I'd highly recommend checking this out after the lecture. So, just to give you some brief history about GANs, the idea of generative adversarial networks has been around for a bit, but it was first coherently sort of put together by this person named Ian Goodfellow, who's in the center image right here, in 2014. And the story is actually kind of interesting. Ian Goodfellow went with a couple of his doctoral friends to a bar in Montreal. So at the time, Ian Goodfellow was pursuing a PhD at the University of Montreal in Canada, and he and his friends were going to a bar to celebrate the successful. I think one of their doctoral friends, had finished their PhD, so it was a celebration, and they were discussing generative models at the bar, and he sort of Ian Goodfellow basically came across this idea of, hey, what if we put two neural networks against each other to try to generate images? And the idea sort of stuck with him during the time at the bar. And as soon as he went home, which was I think late in the night, he stood up and then like coded this. The first version of a generative adversarial network, and surprisingly, it worked the very first time. And he and his colleagues at the university released their paper very soon after. So it's one of those like for sort of uh, it's sort of a surprising instance where the idea in deep learning worked out on the first try, right? It usually doesn't happen like that. So the image that you see on the left is actually an image from the first GAN paper, and these were the sort of images that it generated. Um, so not as good as the photorealistic faces that you saw on the first slide, but it's pretty awesome that a computer generated these numbers. These are all generated by computer. And I have this thing here just as a side note, but if you ever like pursue like take a deep learning class or something in college, you'll probably come across this book, which is currently like the foundational text for deep learning, and Ian Goodfellow actually wrote it, so that's why I included that there. Yeah. All right. So now let's get into what GANs actually are. So generative adversarial networks, you can tell by the name. Generative means generating something, and adversarial means that there's adversaries, opponents. And so in a GAN, there's two neural networks, and these neural networks are called the generator and the discriminator. And we pit them against each other. So to give you an analogy to help you better understand, and actually this analogy was used when in the original paper that introduced the GAN. So you can imagine the generator as a counterfeiter who's trying to generate fake money. And you can think about the discriminator as a police officer who's trying to detect whether or not a certain bill is real or fake money, right? And you can imagine that as the generator gets better and better over time, he or she gets more accurate at printing out fake money, then the discriminator would also get better at discerning whether or not a bill was real or fake, right? So as one system gets better, the other system is sort of forced to become better, and you sort of get this gradual improvement of both of the systems. Now, for our purposes, or for most of GAN applications, we only care about the generator. So the discriminator is kind of there, and we have to train the discriminator. Um, But the generator is what we're most interested in because that's the thing that gets us our images, right? That's the thing that gets us our generated stuff. So let's get more into the details now. So discriminator, when we're training stuff, when we're training the network, gets its data from two sources. It gets its data from this one pile of images, which is from our real images. And it gets another set of its images from the generated pile of images. So when I say pile here, for the real images, when we're training a GAN, we need some sort of training set that tells our network, hey, these are the kind of um, these are the kind of images that I'm looking for, right? So remember on the first slide when we had those generated numbers, uh, the training set there was actually the MNIST data set that I believe either we had a competition that used the MNIST data set. If not this year, then definitely in past years. Um, so that's this real images pile over here, and then our generated images come straight from the generator, and I'll talk more about the generator on the next slide. But we basically get data or images from these two sources, and the discriminator's job is to tell what's the probability that this is a real image. So for all of these images, if the discriminator is doing its job correctly, it would be a 1, and for all of these images, it would be a 0, right? That's the goal of the discriminator. And so this discriminator loss that I have here, um, that should basically penalize the discriminator for getting any wrong answers. So either classifying any of the real images as fake or as classifying any of the fake images as real. So that is what the discriminator is. And during training, what we basically end up doing is conducting backpropagation from this discriminator loss backwards onto the discriminator, right? So we adjust the weights of the discriminator according to this loss function. Okay, now let's talk about the generator. So the generator, as we talked about before, is a neural network, just like the discriminator is, right? Discriminator, hopefully you understood, like it inputs some image, right? And so these would be like you input the pixel values of the image and you output some probability, ranging between 0 and 1. The generator is a bit more complex in that you're trying to generate an image. So the output of your network is actually an image, right? So for example, for the MNIST example, where you're trying to generate like a number in black and white, the number of output nodes in your generator network would be like 784 because an MNIST sort of image is 28 by 28 pixels or 784 pixels total, right? So that's the output layer of your network. Now the input layer is a bit tricky in that you don't really have anything to input if you're generating random numbers. So what you end up doing is just giving some random input to your network, to your generator. You just randomly sample from like a uniform distribution and you give some set of numbers to your generator. That's what this random input is. And so now that we have that put in place, we have what the input to our generator is and what the output of our generator is. Um, you can sort of think about, okay, how do we tell if the discriminator is doing good or not? We can tell, we can measure the performance of the generator by seeing whether or not we were able to fool the discriminator, right? If our images that we generate are very lifelike or very, um, you know, very similar to the real images, then it would be the case that the discriminator would have a hard time discerning between any of the real images and any of the generated images, right? Because the images are so closely related, and so uh, basically our generator loss depends on how well we were able to fool our discriminator. And once we have this loss, which should basically incentivize our generator to get better and better at generating fake images, we back propagate through these through the discriminator and the generator and change the weights here. Note that even though on this path towards the generator's weights, we go through the discriminator, we don't actually change any of the weights in the discriminator when we're training the generator. We hold this part constant and we just change the weights here. So when training again, as we talked about before, we have two networks, and this makes training again a much more complex problem relative to training like a neural network to classify digits, for example, because we have two systems, and the loss or the performance of one system basically depends on the performance of the other, right? Because they're both tied together. They're both kind of playing this game where they're trying to one up each other on every single training iteration. So, in order to account for this, the GAN training algorithm is as follows. We first train the discriminator and hold the generator constant during this time. Then, once we've trained the discriminator, we proceed to train the generator while holding the discriminator constant. And then we repeat. So note that I explicitly mentioned that when we're training one system, we hold the other system constant. It's absolutely essential that you do this, otherwise it's going to be extremely difficult for the systems to converge. Like, it's already hard enough that we have two things that sort of depend on each other, but if you're changing the weights of both of these systems at the same time, it basically makes the problem impossible. So, uh, yeah, that's sort of uh, the key takeaway from this slide is while modifying one system's weights, you have to hold the weights of the other system constant. And as a side note, for those of you who have taken the AI class at TJ, or for those of you who are taking it currently, um, the GAN training process, you've sort of maybe thought about this, but it's sort of like a two-player game, right? Where one player goes or trains, and then the next player trains, and so on and so on, and you're trying to one up the other player. Uh, it turns out that you can actually formalize the sort of back and forth between the two systems as a minimax game, just like tic-tac-toe, just like you did with tic-tac-toe and AI. I won't be going too much into like the game theory formalization here, but you can check out the GAN paper, which really uh, goes into it with depth. Uh, so yeah. Okay, so we've sort of been talking about the loss functions of the generator and the discriminator in sort of abstract, but this is basically the expression that was introduced in the paper. And we use this expression for both the discriminator and the generator. Now, don't be worried, like it might look complicated, but each of these terms is actually something that we have talked about already, so you don't have to worry about it. Uh, One thing to note, though, before we go on to examples to get a better intuitive sense of this expression, is that the discriminator is trying to maximize this expression, and the generator is trying to minimize this expression. So, usually when we have a loss function, we're trying to minimize it, right? In gradient descent, you're trying to descend down the loss function. But in this case, the discriminator is actually trying to maximize the function. So we actually perform gradient ascent, not descent. This is basically, there's not much you have to change. It's just instead of subtracting the gradients, you add the gradients, right? It's not too much of a change. For the generator, it's basically the same thing as backpropagation, like that we talked about before, right? So unpacking this expression a little bit, um, dx here so d, anywhere you see d is the discriminator, and we're sort of writing the discriminator as a function that inputs some image. So here x is a real image from our training set. This would be like a real image of a number or something that we get from like the MNIST dataset or something, and then g of z is our generated dataset, a generated image. So G of Z is a generated image, X is a real image, and D is the discriminator, and that's basically all we need. Here, E and this like EX, and the square brackets basically means expected value. Like from research stats, expected value is just like uh, it's a pretty simple concept, but like you just take the average over a long period of time, right? So basically, we don't have to worry about that too much for this specific like uh, this is sort of we use the expected value thing for the game theory sort of point of view, but I'll talk more about this on the next few slides. Okay, and one important thing to note is that in this expression, the discriminator is involved in both the left-hand side and the right-hand side, right? Um, but the generator is only involved in the right-hand side. So the generator can't actually change what's going on here because the only thing that's involved here are the discriminator and the real images. And the generator has no impact on either of those two things. Um, right? So the generator can only affect this side of the equation. The discriminator can actually affect both, but the generator can only affect this side. Okay, so let's walk through some examples to get a better sense of what's happening. So in this example, this is basically a worst case scenario for the discriminator and a best case scenario for the generator. So let's say, and just to recap, I mentioned that for the discriminator, for all real images, we should assign a probability of 1, and for all fake images, we should assign a probability of 0. So let's say that for all real images, instead of assigning 1, we assign 0, which is the exact opposite of what we're trying to do. And we do a similar thing for all the fake images. Instead of assigning 0 for all the fake images, we assign a probability of 1. So this is about as bad as you can get, right? If you're the generator. I mean, if you're the discriminator. This is amazing if you're the generator, right? Because if you're the discriminator, you're basically getting everything wrong, like everything. And if you're the generator, you're fooling the discriminator very well, right? Because for all the images that you generated, the discriminator thinks that they are, like 100% real images. That's what this 1 means here. So if we plug this in, since we are talking about all real images, the expected value thing sort of goes away. Like we don't have to worry about it. But let's say that um, we plug in, so d of x here would basically be 0, right? Because uh, this is the output that we get for the real images. So we would get log of 0 here, and log of 0, this is a graph of log base 10, right? And if you go to 0, we approach negative infinity, right? The output of that function is negative infinity. So, we're just putting negative infinity here. It's actually never going to be negative infinity because we're never going to get 0.0 because we deal with floating point numbers in deep learning. So it's like basically impossible to exactly get 0.0 exactly. So it's just going to be some very negative number, right? Um, and a similar thing happens here because d, a g of z, is basically, okay, what does the discriminator output for the fake images that we have? And if it's outputting a 1, which is, the exact opposite of what it's supposed to do, we get log 1 minus 1, which is also a log of 0, which is also, here I'm writing negative infinity. It's just going to be some very negative number. And adding those two things together, we have one large negative number, one very negative number plus another very negative number, and we end up getting a very negative number. And so, going back to the previous slide, we said that the discriminator is trying to maximize this number. Now, obviously, if you have this is a very negative number, so that's not very good. The generator is trying to minimize this, so the generator did a pretty good job here. As I mentioned before, the generator can only sort of affect this part of the function, so we don't actually need to consider this when we're training the generator. But I'm just putting this here because it's sort of nice to see that all of the whole thing can be derived from this one expression. So in the second example, previously we looked at the worst case scenario for the discriminator and the best case scenario for the generator. Here we're flipping it. So here the discriminator is performing very well and the generator is not so good. So for all the real images, our discriminator, outputted a perfect 1.0, which is like, as good as you can get because that's what we want. And for all the fake images, it's also doing really good. It's, outputting a 0.0. So discriminator is doing stellar here. The generator is not doing so good because for all the fake images that it generated, the discriminator was able to perfectly discern that these are fake images. So generator is not doing so good here. So what ends up happening is when we plug these things in like we did last time, again we don't have to worry about expected value here because we're saying that this is for all real, it's 1.0 for all real images. Um, so when we say um, when we put log of 1 here, it's sort of hard to see on this graph, but log of 1 is 0, right? And then here, similar thing happens because this is 0, so this term goes to 0, so we get log of 1 again, and we get 0 plus 0. Now, 0 is not a very large number. I mean, like, it's all relative, because previously we had some huge negative number. I mean, some very, very negative number, right? So there, the generator did good. But when we have 0, um, that's basically the best case scenario for the discriminator and worst case scenario for the generator, right? Um, but hopefully this makes sense because 0 is a higher number than some very negative number. So in this case, in this example, the discriminator performed very well with a higher number. It maximized it pretty well. And in the previous example, the generator performed better, and it is trying to minimize this expression. So, hopefully, I just give you like the best and worst case scenario. So hopefully that gives you an intuitive sense of what this sort of complicated expression means. So, wrapping up, what we talked about in this lecture was sort of the basics of GANs. They're sort of like the bare bones that were introduced in the first introductory paper. But there have been a huge number of advancements over the past several years. This is sort of, I think this was an image taken from the first paper that introduced GANs, and this is in 2018. So it's gotten like progress is super quick, and we've gotten to the point where it's extremely difficult. It's almost, I think it's impossible to tell whether or not an image is, at least from a human. As a human, it's impossible to tell like whether or not this is generated by a GAN or not. Some interesting applications of GANs include deepfakes, like what we see here, where you're trying to, be someone you're not digitally. Uh, and some other things. One very interesting application of GANs is that you can generate new training data to improve training accuracy. Um, so if you don't have enough data in your training set, you can actually use GANs to generate fake data, and this can actually improve your machine learning models. So that's super cool. And some other applications include image colorization, so adding color to black and white images or changing the style of images, improving image resolution. Uh, some other applications include like if you have a section of the image that has been completely occluded, you can actually like use GANs to fill in the image. So that's super cool. So there's lots of interesting areas that GANs are being used right now. Hopefully this lecture gave you an intuitive sense of what GANs do and how they work. Thanks for watching.